Okay. All right, let's start our designs. State feedback and output feedback control is almost everything about the basic modern control designs. So we will cover some fundamental concepts in a way that's accessible, hopefully, to most of you. What's the purpose for designing control? You may have your understanding from your previous project. You want to make conversions faster, right? Track something faster, things like that. Less overshoot, smaller steady state. You have a lot of engineering design criteria, right, that you care about. The foundation or theory should tell you is that what essentially you're doing is trying to use your control to modify your system, the closed loop system behavior, so that your closed loop system, in the linear case, okay, has desired eigenvalues. Okay? So you should be able to think your engineering routines or details that you are debugging, tuning, and abstract that out to see mathematically what I'm tuning is just I'm affecting the pose or eigenvalues of my system. Okay, that's the connection between real world and mathematics and control theory. And we will learn, we'll teach you how to do this. Okay, first is the following. Let's look at some kind of a response, typical response you may see in your control designs. But before that, let's first look at this, right? So suppose I don't have a control yet, or I have an autonomous or closed loop system. So control is already been plugged in, right? So the system response to any internal or initial state is a raised to power k times initial state, as simple as this. And we discussed the simple case that we discussed before, then this requires you, I mean, everything depends on, the only thing that depends on k are the eigenvalues. If you write or you kind of diagonalize k, a, then you see that essentially the eigenvalues are the key to determine how the system trajectory responds into the future. And we also mentioned Jordan form, right? So in the general case, not only the eigenvalues, so those eigenvalues appear on the diagonals, but there's other terms also depend on k or change over k. This term will show up in the response after you multiply those similarity transformation matrix. Okay, so the term of the following form is some kind of polynomial of k times exponential of lambda eigenvalues. So all the things, if you mathematically somehow think about this, is nothing but eigenvalues of A that matters. All right. The other term slightly more also matters when, but it's the eigenvalue effect all dominate the entire response. Okay, let's look at some figure. Let's suppose I have a matrix of the following form, okay? This A matrix, by design, I have two kind of complex eigenvalues. Eigenvalue can be complex, right? But they just need to appear in pairs. So in this case, the eigenvalue is, in discrete time, we are dealing with unicircle thing, not the open left half plane, right? So the eigenvalue has a norm. In this case, both eigenvalue, lambda 1, 2, the absolute value is rho. The way I write it is like this, right? So it's the eigenvalue is like on some circle, rho. This is rho. And so maybe this is the eigenvalue, okay? This is my theta. Okay, when theta is 0, the eigenvalue is real because sine theta is 0, so you don't have complex part, okay? Rho may not be 1, by the way. Rho could be anything, okay? Rho is not, so it's not identity. Rho can be smaller than 1, bigger than 1, or equal to 1. And so when theta is half pi, it's completely imaginary eigenvalues. Okay, so now I plot this as k go to getting bigger and bigger. I plot the x response. There are two-dimensional x, right? There's two figures here, but their behavior are similar. And those are the parameters of theta and the rho that I used for each of the plot. Let's say this guy, you can see the typical response, right? It's somehow oscillating a little bit, eventually converge or that kind of die out to 0. That's for theta equal to pi over 5, and rho is 0.9. Okay? From here to here, rho is the same, but the theta has been smaller. Okay? Theta is smaller. What's the difference of these two responses? Less oscillatory, right? 震荡的少一点，对吧？没有乱动了，乱动的频率小一点。Okay, let's further reduce theta to 0. There's no oscillation. Okay, because these become real eigenvalues. There's no oscillation anymore. It's just monotonically converge to 0. Okay, now let's look at this way. So from this guy, I keep theta, then I decrease rho. Make rho smaller. What's the difference now? Converge faster. Okay, and from here to here, I increased. I also studied the effect of rho. Rho become bigger than 1. What you see is diverging, right? This is unstable now. Why? Eigenvalue is bigger than 1. It's outside unit circle. It's unstable. So your system actually diverges eventually. Okay, the rule of thumb. Of course, you can play with this a little bit, but you have to be able to summarize. Okay. So the rule of thumb is summarized as follows. The magnitude, if it is larger, then it will converge slowly. So you want the eigenvalue magnitude as small as possible. Because each time you're multiplying by it, a little bit small can make the converge faster. Okay? So, and the small lambda produce fast response, okay? And the real means theta equal to 0, okay? Real lambda produces monotonic response, while a complex lambda produces oscillatory response. The oscillation is due to the eigenvalues are complex numbers. Okay, now let's think in terms of complex numbers. For complex lambda, the response becomes more oscillatory as the ratio increases. How do we increase? So the more you're close to the imaginary axis, the bigger theta, okay? This guy, if theta is here, no oscillation. This guy is here, almost like infinite oscillation. It's keep oscillating, okay? Pure sinusoidals. So our control goal, I hopefully convince you, our control goal is that becomes how to modify the eigenvalues of your system by control. Okay? This is the fundamental nature of designing controller. Okay, it's different from your experience or rule of thumbs. You may tell this guy, okay, I think you should tune this guy bigger. I think you can tune that guy bigger. Sometimes I see this is better, that is better. So those are experience, okay, based on observations. But here it's based on model and reasoning. Essentially, what you're doing, whatever you're tuning, is modify. If your system is modeled as a linear system, it's modifying the poles or eigenvalues of your system. How much you can modify? What's the consequence? Those trade-offs are the things you need to explore. Okay. So now, I hope that's fine. So all the controls, linear system, state feedback control, they're trying to modify the eigenvalues, right? And for linear system, why it's so popular? Because there's a complete theory for you to arbitrarily control the eigenvalues if your system is controllable. Okay, you have to understand controllability before you can make this claim. If it is not controllable, you wouldn't be able to. Okay, some part is just hard to control. All right, so there's two types of control we need to learn. Both are important. One is state feedback. So all state variables can be measured. It's like what we see before is y equal to cx, where x can be uniquely determined from y by inverting c. Sometimes c is this identity. You can directly measure all the state. That's fine. If you cannot directly measure all the state, then you need to use output feedback. Okay? So by feedback, I'm not sure how you understand feedback. State feedback is a law that it's a controller. If you like to see maybe a diagram, right? So that's your controller. You can draw, say, a controller. That's my controller. But what controller is doing? It's nothing but you send them your measurement, for this case state, and you tell them what your control should be. Okay, that's mathematical representation of control. It's also an input-output pair, right? But the input to the controller is state or whatever measurement available to the control. And the output is that the control action you want to send to your system. So in the sense that in static controller, this is just a mapping from state, your control. So that's called state feedback. And output feedback is that you only know output, and your controller should be, you design your controller. Oftentimes this you need the observer involved. Okay, so we will discuss both cases. Let's first somehow clarify a few kind of important definitions. Let's first look at our state feedback definitions. Okay, so our goal, I want to remind you, okay, our objective is here to drive the state xk to 0. Okay, that's regularization problem, or it's called a stabilization problem. Not tracking, okay? So you want to drive state to 0. Here I use quote unquote 0. That means arbitrary constant number is fine. I can call it 0. If I want to say I want my car to autonomously driving at 70 miles per hour, that 70 will be your 0. You want to make the error to the 70 converts to 0. You have to change a little bit, define your system coordinate for which the origin stands for a desired property. Okay? Let's first look at this case, but tracking will be similar based upon this. Let's first look at most of the control problem we deal with. You can somehow transform it into this stabilization problem. If you cannot, then you need to do tracking problem, but tracking is also based upon the stabilization theory. Okay. All right, so we focus on linear case. So here, generically speaking, state feedback linear case will be just a K. Again, this is a gain matrix times the state feedback, state vector. Okay, it's a linear function. This is a linear function of state. Okay, so everything is still linear. So for example, x could be 2 dimension. X could be x1, x2. Let's say this is the example. U could be multidimensional. U1, U2, U3. Doesn't matter. You may have 2 state or 100 state, but you have a multiple dimension input as well. So our goal is to design the feedback gain matrix K, the setup, right? So this, of course, is a special way to design controller. The control can be arbitrary. It doesn't need to be a gain times something, right? But for linear system, this is good enough. For pure linear system, this is good enough. And sometimes you can find the optimal gain as well. But for nonlinear system, this may not be the case. If you want to see where the term feedback comes from, I can draw the diagram. This is your system. System is mapping from what? U to output. In this case, the output is state. Okay, state feedback means you can measure all the state. All right, and the state will be feedback to this controller. This is my controller. Negative k times x. This is my x, right? Are you with me? Okay. You see a loop. I hope that's good enough to motivate you to think about this as a feedback. There's a loop here. So every time step, you determine this u, you send to the system tell you y, and that y will be feedback to your controller, the same y, okay? And then your controller decide next time step control input. This is a loop, iteratively evolve your system. Now let's obtain the closed loop system. As I mentioned, now your control law is this is AXK plus B times UK. But U, I already decided the format of my U, right? My U is nothing, it's a linear function of the state. What is it again? Negative K, XK. So whatever you see X, you multiply by K. You send it out. It's like a proportional control, P control. 比例控制，只不过是 multi-dimension， 好吧？ You can think about X as an error to your desired state. You see some error positive, okay? Maybe you say, oh, I'm overshoot a little bit. I need to decrease this. It's just like that, simply like that, right? If you see error, you multiply by again, then you send to the system. Proportional control. Okay, if you group this term, this xk, you find it out, this is a minus bk times xk. All right? So this a minus bk is called closed loop system matrix. Is this a matrix? Yes. This is also a n by n matrix. Sometimes I call this a closed loop AC. But sometimes I also use AC, so a continuous time A matrix. But it should be clear from the context. All right, if you have an original ABCD matrix, then you plug in your feedback law, negative k times x, then your closed loop system becomes, what it becomes? It becomes a xk plus 1, the closed loop trajectory is AC, or A minus bk, times xk. There's no control anymore. You see what I mean? I also mentioned before, sometimes you don't have control, not because you don't have control. It's because you plug in your control law. So everything depends only on your system state. Okay, this is called closed loop control system behavior. It's like A minus bk times xk. Okay, now the question becomes, what's a good control? Can you tell me? You need to think, all right? You are now trying to learn the problems. Of course, we can only solve problems under some assumptions. Now our assumptions we stay with linear system and the linear feedback. Now what is a good K or good control? You need to tell me what's a good eigenvalue is, right? We will learn a little bit about that, what a good eigenvalue is. And so all your purpose now is use A may be bad, maybe even unstable, okay? All my purpose is trying to use my K. I have design variable K so that I can modify or shape the eigenvalues of A minus BK. Okay, that will determine my closed loop response of my X trajectory. Okay, so that's the so-called, I would say, eigenvalue assignment problem or pole placement problem. Find K so that the closed loop system A minus BK has the desired set of eigenvalues. So the key is I want to know the eigenvalues of A minus BK. Okay. We didn't review eigenvalues. I assume that you are very familiar with eigenvalues. How to compute eigenvalues? Delta. Characteristic polynomial of a matrix, right, gives you the eigenvalues. So if I want to know these eigenvalues, these are the solution to lambda, this AC of lambda, eigenvalues, characteristic polynomial, this determinant of lambda I minus A, which is A minus BK in this case. Okay? This guy equal to 0 gives you the roots. And the roots are the eigenvalues of A minus BK. So everything boils down to, okay, how can I use K to modify the characteristic polynomial of A? All right. So that becomes purely a mathematical or linear algebra problem. As I mentioned before, modern control is an exercise of linear algebra in the context of control applications. Two keywords are important. The theory mainly builds upon linear algebra, but the context are important, right? So how do you formulate real-world problem into control problem and solve it? So that connection is also important. Okay, let's look at the simplest case. Whenever you want to do research or solve problem, we start with a simplest test or toy example, typically people call that, to understand the whole procedure. Single input case means what? B is Rn by 1. Okay? Yes. There's one kind of a single input system that are really, really important. It's called controllable canonical form. Have you heard about this? 没有，是吧？没有。我们做那个 transfer function to state space 变换的时候呢，那个东西就长成这个样子哈，就是一个 controllable canonical form. If you haven't heard about this, this is nothing but a particular form of the AB of this form. Okay, B is all 0 except the last one, and A is like this. I think those kind of matrix you have seen this before. Okay, so all the diagonals are 0 except the last row has non-trivials, and the off diagonals are 1s. Okay, so the system is in controllable canonical form and is always controllable. So if I can put a system in this form, suppose it's a very stringent form, right? If I can put my system into this form, then this system must be, this form of the system has to be controllable. That's why where the name come from, okay? So let's check. So MC bar is B bar, B bar, A bar, B bar, all the way to A bar and minus 1, B bar. Okay, you see why we need to learn controllability now. Okay, let me show you by example. Suppose I have A bar equal to 0, 1, 0, 0, 0, 1. Let's say A, B, C. The last row is non-zeros, but any row except last row are of the already determined the format. Okay, and the B bar is 0, 0, 1. That's a controllable canonical system. If I have this kind of matrix, and you can find it out. MC equal to n equal to 3 in this case, right? It's B is 0, 0, 1. B times A is A times B. Sorry, A times B is 0, 1, C. Okay, and A squared times B, which is A times this guy again, will be 1 C B plus C squared. Okay. The key is that you see those elements does not depend on ABC at all. Okay, and this system is this always, okay, this rank of this MC bar is 3 for any ABC. ABC can be all 0, that's fine. All right, whatever ABC is, this guy MC bar is always rank is 3. All the 3 columns are linearly independent. Are you with me? There's no way you can make it independent by choosing different ABCs. Okay. So this is always true. So one can show that, I will say that one can show MC bar is always full rank for any A bar, B bar in controllable canonical form. In controllable canonical form. All right. It turns out design against to assign eigenvalues of a closed loop system can be done very, very simply by hand, even by me, okay? I'm really bad at calculations. By hand for a controllable canonical form system. Everything you can write on a piece of papers. And for any controllable system, you can always transform it into a controllable canonical form through change of coordinates. Okay, so that's the one. You have something, it's really simple to design. All the complicated case, you can do a change of variable. I will teach you how next time to transform into controllable canonical form so that you can design the simple case, then move back to your real world. That's the whole procedure. Again, you will never use it in reality because there's packages out there or functions in MATLAB or Python you can directly call, okay, but you have to know what's going on there so that you know the limitation of those functions. Whenever you're not satisfied, you can modify or use other approaches, okay? I think there's 2 more minutes left. I think we can stop here. Because we go over 2 minutes after the first part of the lecture. Okay, that's enough. Let's go back to lecture note 5. Last time we started lecture note 5. This lecture is about designing state feedback and output feedback control. Okay. The very first part, I think I emphasized quite a bit, is that the purpose of design control, build the control, right? Control is try to design controller to influence your system output so that you have desired output. The first question we need to answer is that what really affects or determine the system response. If we don't have any input, the case we showed last time, that the system response actually depends only, almost primarily on the eigenvalues, all right? Eigenvalues of the A matrix. So designing control is almost like shaping or changing the eigenvalues of the closed loop system, okay? There are two confusing parts that I think people may ask, and some people ask me after class. I may clarify a little bit here before we move forward. The first one is that the discussion before we said it's xk, we assume the response. The figure I showed before, for example, those figures, that's a response. We argue those response primarily determined by the eigenvalues of the A matrix, right? That's what we discussed last time. But that response is under what? Under zero input. Zero input or zero control, so that UK is always 0 for OK. Okay. So that may not be as convincing as I say, if I have a system, I have a non-zero input, does the system response still primarily depends on the eigenvalues? What do you think? So what about, some students ask me, okay, what about UK is non-zero? Of course, when you design controllers, you hope your system, the behavior can be changed by designing different input signal, right? For example, step response. Okay, so if it is non-zero, for example, that's step response. Step response, it means UK is always 1. Okay, it's a constant, unit constant. It can be 2 or 3, that's fine, but that's a unit step response. In this case, we have learned, right? So the state, I think it's called state solution, state space trajectory solution, is 0 input response, which is A raised to the power K times initial state. That's the 0 input response. That's the response mainly due to non-zero initial state. Okay, plus 0 state response. That's the response mainly due to input without any initial condition. This part has a convolution, right? This part has J from 0 to K, I forgot what it is, K minus 1, right? Okay, A raised to the power K minus 1 minus J, B U of J. Okay, that's the formula we derived with you. Okay, I think this is very simple to derive. In continuous time, it's a little bit hard to derive. You need to do matrix exponential, but in discrete time, you can just summarize this summation formula. And I want to just write it out so that you can also see the behavior of the system. So this is nothing but J from K minus 1. Let's assume A is still Tj T inverse. This is a Jordan block. That's the diagonal has all the eigenvalues, all right? So that will be, if you just remember, we have tried this many times. I don't want to repeat them. So it's Tj K minus 1 minus, that's a small j, is a summing index. Okay, this capital J is a Jordan block. T inverse, this is A K minus 1 minus J. All right, times B is constant, suppose. Okay, this part, whole thing times U. U is 1, right? In this case, step response. Let's say it's a vector, or ones, right? It's constant. Let's times, let's assume this scalar case to simplify the discussion. This is 1. All the time steps, the input is just 1, okay? So what do you think? So this part we discussed last time, it really depends on the eigenvalues, right? The response, what do I mean by response? Response is a time varying signal that depends on k. K is my time index, right? How the system evolves over time, k is what we care about. So this part is also related to all the eigenvalues of this A, right? But it just have a summation of the power series. Okay, so every term here is a function, it depends on the eigenvalues. So in this case, it's still the same thing. If the system is stable, this part will convert to 0. Okay, and this part, I would say, let me just summarize. You can simulate the system behavior by yourself. Let's just say, if a system is stable, stable means all the eigenvalues, the magnitude lies smaller than 1, right? So this part will converge to 0. So a raised to the power k, this will convert to 0. That's the definition of asymptotic stability for a state space form. Okay, and also that means lambda i's are all less than 1, right? So essentially, this summation term, if you want to only sum, this would be, I'll call this term, so a raised to the power minus this summation b times 1 is nothing but t times summation j k minus 1 minus j t inverse times b. Okay, I'm just summing this out. This part is almost like, if you think about eigenvalues, so this part of lambda 1, k minus 1 minus j, suppose it's diagonalizable. I want you to think about simple case to gain insight, right? The summation over j, this part, okay? J. It's called a partial sum, right? This case is like that. So if lambda I is less than 1, so if, for example, let's say summation lambda, for example, summation, just give you a sense of, for example, summation of half k minus 1 minus j over j, it's a constant eventually, right? No matter what k is. This is a partial sum, right? Are you with me? So as k go to infinity, this partial sum will convert to, this will convert to k, as k go to infinity, this will convert to something like, let's think. Minus j, is that, huh?
Like some mathematics in the high school.
Yeah, exactly. So it's a power series. Let j equal to 0. J equal to 0, it is what? Half of k minus 1.
Yeah.
K equal to, j equal to k. Is 2. Right? So, and every term, it's, I think it's just, well, you can use power series. Eventually, this converts to a constant. Okay, as long as this part is smaller than 1, it's converted to a constant, finite constant. And how fast it converted to constant depending on this thing, right? The smaller this part is, the faster it converts to. All I want to say is that once you have non-zero input, okay, the system response still depends on the eigenvalues of A. Okay, but you may not say all the output convert to 0, but eventually will convert to some constant, but the transient behavior, 站态响应, 顺态响应, okay, will depends on how small the eigenvalues is, right? So you can calculate these numbers. You are better than me for those kind of calculations. Okay, so that's the first thing I want to mention. So even with, that's why we only care about the eigenvalues of A. That's the only thing that depends on K, because we study response means study something, the system trajectory or state at different time K, how that thing change over time. Okay, Now, the second part is, let's see, what do I mean by closed loop? Okay, some student asked me after class, what does this diagram mean? I think it's pretty straightforward, but I'm not sure if, do you have any questions about what do I mean by closed loop? There is a loop.
And
It's closed, okay. Let me explain that a little bit more so that you can hold on. I think by closed loop, you all learn from your classical undergraduate control class, right? So suppose you have a block diagram. You have system 1. You can have system 2. Okay? Maybe you have something like this. This is system 3. This may be a summation. And this block diagram, you know how to reduce this block diagram to a single block diagram, right? You can represent, I mean, this is composing different subsystems, make a whole overall system. So you can have from the input here to the output here, you can have the same equivalent block. That's the total system, overall system. Okay? You can do block diagram reduction. I don't know what you call it, right? You know, you learn how to do this. Do you think this is a loop?
No.
You see some kind of loop here, right, by figure, but is this a loop? Is this a feedback?
No feedback.
No feedback, right? But anyway, you know the overall system can be represented by a single block diagram, single system, right? But we don't call this really a loop. And typically loop means specifically that you feedback the output of your plant or for your target system to your controller, okay? Suppose this is my controller system, and this is my plant. This is my Y. Typical loop you will see is like this. This is feedback, negative feedback, right? So this is your reference. This is your output. That's maybe is this a feedback loop?
Yeah.
The reason it's called feedback loop is mainly because there's a loop and this Y becomes, coming back, the input of the controller or influence the input of your controller, okay? If I have a plant, if I have the loop like this, let's say I have a loop like this, it's still a feedback loop. Your system depends on itself, okay, output. But the feedback control system or closed loop typically means the output of your plant somehow gets used or determine the input of your controller. That become a closed loop system, right? In this way, the system is a closed loop, but typically, more generally, let's say we have the reason I'm talking about this is because of the homework. I think some students ask me the homework, how to simulate. For example, this homework, in the homework, we ask you to simulate a feedback connection. And some people, maybe in the WeChat group, and they say this is not, we haven't learned this in class. Actually, we have everything you need to do that problem. So I don't want to teach you everything about that, but I do want to mention a special case so that you will know enough to do that homework, okay? Let's use an example. Let's do a generic. I don't want to do exactly the same thing as the homework says, okay? Let's do an example. Let's say I have two systems. System 1, System 2. The output of System 2 become the input of System 1. Okay? In the homework, I ask you to do this in state space form and simulate in Python, okay? That's what I ask you. In Simulink, it's very easy, but in Python, that you have to know everything before you can write the codes, okay? But now I'm doing this one, okay? Suppose by modifying my code for this one, you will be able to simulate this for sure. Okay, that's the best I can do, the best hint I can give you. All right, there's two things I can do, okay? The method one is that suppose system one is xk plus 1. Let's call x1k plus 1, a1 x1k plus b1 u1k, okay? And y1k equal to c1 xk. That's my first system, state space form. System 1, and I have system 2, so it's x2k plus 1, a2 x2 xk plus b2 of u2k, and the y2 of k equal to c2 of x2 of k. Sorry, this is x1 of k. I have two systems. Each of them may have different dimension. I didn't say it's the same. But in order for this connection to make sense, what do you think the only requirement I need is what?
X2k plus 1 have the same dimension.
No, right? So this signal has to be the same. Means what? U2 equal to y1. So these two signals have to be of same dimension, all right, in order for my connection to make sense. And this guy is U1 has to be equal to Y2. That's the only thing, right? These two things has to have the same dimension. Let's assume they're just dimension of 1. They're scalar, single input, single output. Okay, so now I want to say what is the overall closed loop system model. Can you derive it? The closed loop doesn't have any external input anymore, okay? Because everything is in the loop. There's no external, it's different from this guy now, okay? Doesn't have an external input. It's basically an autonomous system that depends only on the initial state, okay? That's called my closed loop system. Y, all right? This is my Y2, will be my Y. How to derive it? Can you derive it? Yes. Very easy, right? You just make connections. So let's see, this guy, but in the overall closed loop system, my overall state, X, I need to put these two states together, X1 and X2. Each of them may be several dimensions, okay? You see what I mean? This guy, X1 may be Rn1, X2 may be Rn2. So overall, this is Rn1 plus N2. I hope you are fine with those vector notation now. Okay, so all I need to derive is how the X, the whole vector at k plus 1 depend on the vector at k, right? That's it. So I will say xk plus 1 equal to x1 k plus 1, x2 k plus 1, right? Now I need to relate at time k plus 1 to time k. That's the state update equation. So this will tell me this guy is a1 x1 of k plus b1 of u1k, right? I can just directly plug in this guy. u1k is y2 of k. Are you with me? That's exactly what the connection means. Okay, so this guy is y2 of k. But you know y2 of k, I'm skipping steps. y2 of k equal to c2 of x2 of k. Are you with me? This guy is y2 of k, which is u1 of k. All right, I just don't want to repeat too many steps. The next one is similar. it's this is A2 x2 of k plus B2 of U2. U2 is Y1. Y1 is C1 x1 of k. Okay, so overall I will have, now you can do the kind of a block type of composition. So this is nothing but A1, the whole overall system is what? x1 k, x2 of k. That's my overall state vector. Okay, the state dimension actually increased because you combine the two dynamical systems together. This is A1. What about this A1? This guy is B1, C1, C2. This is the second row is x2k. This is B2, C1 times x1 plus A2, x2. Okay, I derived this. So this will be my A closed loop. In other words, the whole closed loop dynamics is xk plus 1 equals to A closed loop times xk. There's no external input in this case, all right? For the homework, you need to derive that for your controller, whatever. But I think this is, the hint is strong enough so that you can figure things out. Oh, all right, so if you simulate this in Simulink, for example, or in Python, whatever, it's equivalent to simulate a single dynamical system on Rn1 plus N2 extended state space. It's the same thing. They're exactly the same. If you start from the same initial condition. Any questions? No questions. This is the simple, right? So let's give you, I said it's a strong hint, right? So I have to give you code. Let's do some coding. Can you see it? I have two matrices, A1, A2, B1, B2. I will upload this code to our website. Okay, right after class, so you don't need to wait. Okay, and I have a B1, B2, C1, C2. That's my two system. I don't have a direct fit through B. That will cause some problem. Okay, that's when you simulate a Simulink model. Sometimes they will complain you have algebraic loop. That's when you have direct fit through. That's something. I think once you write the code by yourself, you'll figure that out. Okay, that's two systems. Let's see how we can simulate them. And the first approach, let me think. This is I'm specifying the times and the output of the system. Let's say the first approach. This is the first approach. I just derive the closed loop dynamics in the extended space, right? So I can simulate as if it is just a standalone dynamical systems. So construct a closed loop system. I'm just AC is the closed loop, is ACL closed loop, which is A1, BC, B1, C2, B2, C1, A2, right? And you can construct this very easily using NumPy block, okay? So you just put them, if there are dimensionality matches, you can simply put them as if you're constructing a 2x2 array. If those are numbers, you think it's 2x2 array. If those are blocks of a compatible dimension, they are just a block-wise system, that like what we did here. In this case, everything is 2x2, so this will give me a 4x4 matrix, right? And the C is, oh, I haven't derived C yet, right? So my output is my Y2 output, okay? The output of overall system, this Y, is just the Y2, okay? So this is nothing but 0 C2 times x1 and x2 of k. Okay? Is that clear? So those are block matrix. Okay? In this case, my C is zeros and C2. That's it. Okay? Then I can simulate my closed loop system. In continuous time, you need to call the ODE stuff that we mentioned that in class as well. But in discrete time, everything is just a for loop. Okay? I can simulate. It's just at each time you need to update. You just need to do some calculation. Let's do this process. So initially, I just initialize the vector, the state vector, which is 4 by n. That each column is the 4 by 1 vector representing the state at that particular time. I'm initializing. This is the first vector is 1, 1, negative 1, negative 1. That's the initial state. And for Ka in the range, I think I simulated 100 steps. And I compute the Yk is CK, closed loop K times Xk, and Xk plus 1 equal to AC times Xk. That's it. All right, I'm just doing this. You can, is that working? Yeah. So this system is stable, but it's oscillating a lot. All right, when I connect these two systems together. Okay. Typically, we'll simulate a connection of loss-lose blocks. You don't construct extended thing, okay? In this simple case, we can do this by hand. If you have 1,000 or 100 of blocks together, connected together, I don't think you can derive them, okay, to simulate directly a closed-loop system. Actually, I think you just travel in time and up. I just want to show you the simple case that you can use either, in your homework, you can either use this first approach or this second approach. Let's say this is second approach. Just simulate individual blocks. Okay? I think I commented out. So let's do this. What I'm doing now is that I simulate I treat each of these as separate blocks, okay? So, but their dimension will be lower, right? Each of them are 2-dimension now, all right? So x1 is 2-dimension, x2 is 2-dimension, y1 is 1, y2 is 1, and the u1, u2. Each block has its input and output and its own state. Are you with me? Okay? There's no magic. You just simulate another for loop. Okay, I don't need to derive anything in this case. What does the for loop do? First of all, I need to compute y1 and y2. The output, initially x0 at time 0, think about k start from 0 to 100, okay? In this case, 99. Okay, first, at the initial state, because you have initial state, you can compute y. Okay, you can compute y, and then the connection only tells me u1 is y2. Okay, u2 is y1. That's our relation. Do you remember? This is u2 is y1, u1 is y2. Once I figure that out at any time k, I can compute or evolve my system to the next time. Right? That's it. State update. So x1 is a1, x1 plus b1, u1. The connection somehow got determined by what? This part, equality. Okay? And this y2 is nothing but y1. This u2 is just y1. Okay, then you can evolve to the next time step. The next time you can compute this. If you have D matrix, that will cause problem. Okay, because at time 0, think about time 0. Your initial state is given, always given. But you don't know the input yet. All right? That's called direct feed-through. So your input directly impact your output immediately. Okay, so in order to evaluate your output y1, you need to know u1. Okay, You need to know U1, and U1 depends on maybe Y1 again. There's a loop typically, all right? Somehow you need to figure out how to resolve that loop first of all. Okay, let's not worry about that case. In your homework, there does have one, the PD controller has direct feed through term, but it's only one direct feed through. I think you can figure it out. Okay, if I have two direct feed through, then the loop have an algebra loop. The hint I'm giving you, I think that's strong enough, all right? So you can figure that out. In your homework, I think you can follow this structure. You can simulate this. You don't have to derive the whole overall system. If you want, you can of course derive the whole overall dynamics as well. So let me simulate this part again. I think I call this Y2, right? I use the green. So let's simulate the whole thing again. This is the green, this is the red. If I put them together, they will be exactly on top of each other. All right, the two approaches give me the same thing. All right, I hope that's enough for closing the loop. Okay, closing the loop is just assign the input of some block to the output of your plant. Okay, especially that's the case when you connect your output of your plant to the controller. Okay, now I think I clarified two things. First of all, no matter you have input or not, your system response depends primarily on the eigenvalues of your A matrix. Okay, that's my first argument here, although I didn't finish all the calculations. Okay, you can analyze this way, and everything depends on K depends only on the eigenvalues of A. Okay, the second thing I want to make sure is that closing the loop is nothing but sending the plant output to the controller, and all we care is what? Now, is design is control format so that the closed loop plant will have desired eigenvalues. Okay, in other words, suppose my system 1 is my controller, right? All I need is that to modify or design this guy, system 1, so that the ACL has desired eigenvalues. The one I see here, I don't like this response. Do you like it? You don't, right? How do we modify system 1 so that the response, I cannot modify my plant, I cannot modify system 2. This guy I can design, for example. Then I can use 1 to impact this guy, all right? For example, if I say the system 1 is changed, let's change the system 1. Let's change this the number 1, right? The whole closed loop behavior will be different. If I run it again, it's different. Is that worse or better? I think it's worse even, right? Okay, so if I make this guy different again, I have unstable, right? That's the tuning you see, right? So typically you would tune these parameters and to see response. But what we're doing here, you can analyze the closed loop dynamics so that you know ahead of time what are the proper design for system A, which is your controller. Okay. I think that's enough. Let's jump into the design part. In this case, we start from a canonical setup. Okay, the controller depends only on the state, full state, which is negative K times X, which is called gain matrix multiplied by X. X here, as I mentioned before, we are talking about regulation problem. That's X represents the error vector. Okay, the error from your desired value, which is 0. X, no matter what your desired value is, X always represents the error, okay, in this class so far, okay. So now let's focus primarily on how to design this controller, negative Kx, so that the closed loop system, which is AC, has desired eigenvalues. All right, so now let's, I think last time we stopped roughly here. So the single input case, we can do everything by hand. I think that's, at least in the midterm, I will test do this. By hand, design your controller so that you can place the eigenvalues of that correspond to a good response. Not tuning, not see and watch and see and tune, not that, okay? Ahead of time, based on the model, you design again, and you verify it works. Okay, that's the thing I want you to know. Okay, last time we start here, that's simplest case for your design is the so-called controllable canonical form that we mentioned that before is of this form. One thing we checked last time is that any system, AB, of this form, the controllability matrix is non-singular. It's full rank, it's square, okay? It's full rank, and it's non-singular, so that you can invert it. Okay, so that's why it's called controllable canonical form. It's always controllable, right? Why this form is so important?
It can be derived from the transfer function of
That's not why it's useful, because well, we learned that from transfer function to state space change, then we can construct controllable canonical form. The reason is really useful is because of the next property. Okay, because this particular form tell you everything immediately about your eigenvalues. Okay, because we care about what? Eigenvalues of the A matrix. So let's see, there's a property of the system, of this form of A matrix. The characteristic polynomial, you know what characteristic polynomial is, right? We somehow show this a few times. This is very important. The characteristic polynomial of this guy is a polynomial of nth order. It has n coefficients. All the n coefficients just almost be determined by the last row of A matrix. So this A matrix of this form, the only non-trivial part is the last row, right? All the other parts are fixed. Depending on dimension, it will have fixed numbers. Only the last row matters. Let's check this property, okay? I'm not sure whether you learned this from your linear algebra class. Let's check. I don't want to prove this for you, okay? So A bar lambda. What's the definition of characteristic polynomial of a matrix? Determinant of lambda I minus a, in this case, A bar. Okay? This will be a nth order polynomial which has all the coefficients, and the coefficients will be determined by this guy. So I would say this guy, the roots, I just want to recall this fact. The roots of characteristic polynomial of A bar, any polynomial, they will have a root. Okay? The roots of this, that means the solution of this polynomial equal to 0. Okay? Are x of A bar. Okay? These are simple facts. I assume you know. If you don't know, then you memorize this for now. Okay? I didn't say anything new yet. Now I'm going to tell you, for this kind of A bar, the polynomial is already specified by the last row of this A bar matrix. I wouldn't show you in the general case. I just want to convince you with a simple example so that you believe me. I think you believe, but walking through the steps, you know exactly what I mean. A bar is, let's assume, that's a 2 by 2 matrix. So it's 0, 1, negative 1, 2. So in this case, n equal to 2. All right. If I match those coefficients, what do you think alpha 1, alpha 0 is?
1. Positive.
Xiaohan. Positive 1, negative 1. Positive 1, okay? Why? Yes. All right. What about lambda alpha 1? Negative 2. What about alpha 3? No, alpha 2. Alpha 2 is always 1, right? In this case, it's the leading coefficient, all right? So in this case, we don't care about this. So the leading coefficient of polynomial, I always normalize this guy to 1, right? Okay, that's... According to, I don't want you to do the determinant yet. I want you to say, according to this fact, I will say lambda character polynomial alpha, delta a bar lambda should equal to what? Lambda squared. The first order is negative 2 lambda plus 1. Are you with me? I didn't do anything yet. I'm just copy the formula. Okay? And I didn't do the determinant. Okay? So if this is true, then that will be my characteristic polynomial. And if you don't believe, let's check. Let's do the formal way. What's the formal way? Determinant of lambda I minus a bar. That will be determinant of lambda times I is lambda 0, 0 lambda. That's lambda I. Okay? Minus a bar. What is a bar? 0, 1, negative 1, 2. Okay? So if I do the subtraction, I will say this is lambda, this is 1, negative 1, right? So this is 1, lambda minus 2. Can you check the determinant? 2 by 2, that's the maximum dimension you can check determinant by hand, maybe. Me too, by the way, I don't. So this is lambda times lambda minus 2. Minus 1, which is plus 1. Which is lambda squared, lambda plus 1. This is the same as we claimed. If all this form, the characteristic polynomial coefficients are completely determined. That's all this form means, okay? Because of this, the design of controller will be very, very simple. We will start to do this after the break, okay?所以我们基本上每学一个东西，我都要写个 code 给你过一遍，好吧 ？All right, let's get back to this part, abstraction part. Okay, let's see how to design it. So as we mentioned before, all we care is this the closed loop A matrix eigenvalue. Okay, and for now. Let's say we have a controllable canonical form, A bar, B bar, right? A bar may not have the desired eigenvalues I want. All I can do is to design K. The only design parameter is here, right? This is design variable. 你要调的东西就是这个 K。你们都调过那种东西吧？我的学生调起来都是很苦的。如果真的调的话，对你这个系统一无所知的话，那就是纯是 labor work。调一下看，而且还很容易入迷调的。这是我感觉确实是调东西容易入迷，因为你不需要想，它就是调一下看，哎呀好像不行，再调试那个，就你很容易调一天，但啥也没有，就感觉是这个感觉。你们要调过就知道我在说什么。但你真的进来想是很难的，你要把它抽象出来想，分析问题，这个能力是很重要的。你光调其实是很容易的，你找个中专生，哪怕小学生，你就调给他记录下来，也是 OK 的啊，他没准比你精力还好，比你更能熬夜调。Okay, so design parameter. Okay, I don't want to tune it. Okay, I want to design it based on theory or principled way to design it. Okay. So the goal is that mathematically what this means is that if I have this design variable, how much I can change the eigenvalue of A bar to my desired eigenvalues. Okay, that's the question we need to ask. In this case, it will be very simple because, let's write it down, okay? Closed loop A bar minus B bar K bar. K bar is the design variable, okay? Suppose it's, if this multiplication need to make sense, K has to be Rn, 1 by n, right? Because K need to be multiplied by state vector, okay? 1 by n. Okay, so B is what? This is n by 1. Can they multiply? Yes. What you got? N by n matrix. All right, 2 vector almost multiply. You get 2. This is rank 1 matrix by default. Let's see, this is 0, 1, 0 all the way 0, 0, 0, 1. I assume you can filling up all the details for the rest. The only thing matters is minus 1, minus alpha 0, minus alpha 1, all the way to minus alpha and minus 1. The only last row matters, okay? B is a constant matrix, always have the same form in canonical form, okay? 0, 0, all the way 0, except the last element. K, as we assume that there are n vectors, n gain numbers. I need to determine K1, K2, all the way to Kn, n numbers, right? So what do you think the overall, if you do this, all the first, the n minus 1 rows will eventually multiply by K will be 0, right? So in other words, the A bar above, except the last row, all the other elements do not get changed. No matter what K you choose, they will not affect the first n minus 1 rows. Okay? So the first n minus 1 row remains the same. So I will say this is 0, 1, 0, 0, 0, 0, 1, 0. Okay? All the way to here, except the last row. How the last row will be changed? Minus alpha 0 minus K1. Okay? It's just index issue. They start from 0 and start from 1. Actually, that's just the first element of the 2 vectors. I think I may need to, this is negative alpha 1 minus K2, dot, dot, dot. Negative alpha n minus 1 minus Kn. Okay. So now I'm claiming this is almost like the same form as the controllable canonical form of the A bar. Okay? It's of the same structure. It's just that all the alphas got changed. Okay? So I can directly, based on the fact, linear algebra fact, I can directly write down the characteristic polynomial of A closed loop. Okay? Only last row matters. So the A closed loop now is not only n minus 1, it has Kn this term, right? Plus n minus 2 is Kn minus 1. I'm just using that fact again. Okay? Any questions? So now what you can see, by changing, I will say, let's say change by choose K1 all the way to Kn. We can modify it, completely determine that. No matter what alpha 0, alpha 1, alpha n minus 1 is. I can select K to offset them, to completely redetermine the coefficients. I can completely determine the coefficients of lambda closed loop. Okay? the closed loop characteristic polynomial can be arbitrarily designed. That means completely determine the coefficient. If it's fixed, then the x will also be fixed, because eigenvalues is the root of the characteristic polynomial can be arbitrarily designed. Then the eigenvalues can be arbitrarily designed as well. You see the logic? Let's do example. Not example yet. Let's study the procedure. So we start from the goal. Okay, the goal is, let's see. Suppose I have eigenvalue desired. I have n desired eigenvalues, lambda 1, lambda n up to. Okay, how do we choose k bar so that the closed loop system will have desired eigenvalues? First of all, we need to find the characteristic polynomial for the closed loop system of the desired closed loop system. Okay, so because what we want is that I want the closed loop system to have lambda 1 up to lambda n. Okay, then that immediately determines the desired characteristic polynomial of closed loop system. Let me just give you an example. Suppose I say I want lambda desired. I say 2. Okay, 1 is the first one is 0.1. The next one desired. Okay, desired 2 is negative 0.1. Okay, suppose. All right, that's what I want. Maybe next lecture will tell you what are a good desired eigenvalues for desired closed loop behavior. But now let's assume this 2 arbitrary numbers is what we want. Then I can directly write down the closed loop characteristic polynomial, because the desired characteristic polynomial would be lambda minus 0.1, lambda minus negative 0.1, which is plus 0.1, right? This is plus 0.1. So overall, I have lambda squared. This is 0 times lambda minus this. Okay? So these two coefficients are the coefficients of the desired characteristic polynomial. The roots and the coefficients has one-to-one correspondence. If you fix the roots, you fix the coefficients. You fix the coefficients, you almost determine the roots already. Okay, these two are one-to-one mapping. Okay. So in this way, in this case, I have alpha star. I will call it alpha star 0. It's negative. This is the 0th order coefficient. Alpha 1 star is 0. Are you with me? So those are the coefficients that I want my polynomial to have these coefficients. But we may not have it. Okay, initially we are given is alpha n minus 1, alpha 1 and alpha 0 may be different from this alpha star. How we should do? We should choose k to make up the difference. Okay, so basically by choosing these two match coefficients, so basically we want to, for example, we want to choose k bar, which is k1 all the way to kn, such that if you want to list, you want to kind of write down the equation, that will be, I want my closed loop characteristic polynomial equal to my desired, that's my design, okay? That's my desired characteristic polynomial, okay? I want this guy to be the same as the closed loop one. I can always do this by matching coefficient, okay? I can match coefficient by matching coefficient, 匹配这个系数 coefficient. Okay, what we can find out is K1 should be equal to, what is K1? I need alpha star 0 to be the 0th order coefficient. Now I have alpha 0. Okay, so I need these two the same. So K1 is alpha 0 star minus alpha 0. K2 is alpha 1 star minus alpha 1. I mean the index a little bit confusing, but I assume you can handle this. This is and Kn is alpha n minus 1 star minus alpha n minus 1. Alpha star is what we want. Alpha without star is something we have now. Okay, so K is the difference we need to make. Okay, so that's exactly placement. We're done. Okay, let's do an exercise with numbers. I know you like numbers better than others. So suppose I have a system. Is this in controllable canonical form? Okay, it's a 2 by 2. It's in controllable canonical form. Okay, now the question is that we want to find the K bar, which is K1 and K2, such that closed loop, the eigenvalue of A bar minus B bar K bar. The eigenvalues is what we want. It's 0.5 and negative 0.5. If A bar already have these two eigenvalues, then we don't need to do anything. K will be 0. If A does not have this desired eigenvalue, I need to design my K. That's the control part. Of course, you can tune to see what's happening, but it's better you know how to calculate them. So this is step 1. Let's follow our steps. You see, we have 2 steps only, right? The first step, we start from our goal, objective. What's our desired? These two, right? So we can directly write down the desired characteristic polynomial. So lambda desired. So delta desired lambda is lambda minus 0.5 plus 0.5. Okay, which is lambda squared. It's 0 again. Okay. Somehow I like those numbers. So this is negative 25, right? 0.25. So I know my alpha star, what is it? Alpha 0 star? It's okay, and the alpha 1 star is 0. Now you like formulas. Now you can plug in formulas. I hope you don't remember formula, but so step 2. We have currently alpha 0 is what? Without any control. This is my negative alpha 0, right? So alpha 0 is 1. This is my negative alpha 1, which is alpha 1 is 2. Okay? So there's a discrepancy between what we want, the star, with what we have now, which is without star. So overall, I would say K1 has to be equal to alpha 0 star minus alpha 0, which is negative 1.25. K2 is alpha 1 star minus alpha 1. Alpha 1 star 0, alpha 1, this is negative 2. Okay? I hope that's fine. That's our design. Okay, so K is what? So K bar should be what? Negative 1.25 and the negative 2. Let me do this. So now I already have my design, which is negative 25, negative 2. That's it, the design. We can check our design. Check. How to check? Did you meet your goal? Okay, we need to check it's, let's say we have closed loop eigenvalue, which is A bar minus B bar K bar, which is 0, 1, negative 1, negative 2. That's the first A bar, minus B bar, which is 0, 0. B is 1 times K, so it's a negative 2. If you do the subtraction, you will find 0, 1, 0.25, and 0. Okay? I think you can check that now. Okay, so you can check the determinant of this A closed loop, lambda I. So this is lambda I times A closed loop bar will be lambda square minus 25. Okay, you can check that. I think you can do it. This is verify yourself, similar in the way that we did in the previous slide. So now my closed loop eigenvalue will be lambda equal to plus minus 0.5. Okay, it's correct. What do we want? So simple, right? Are you going to use this in the real control design? No. Not at all. At least I don't think so. You will use MATLAB or Python command package, but you have to know what's going on. That's the difference. You know what's going on. All right. So that's the design procedure. You may think it's cheating, right? We start with this very special form, this, controllable canonical form. Most likely, the system you encounter in real life is different, right? How we can do the design. What do you think? It's often the case when you encounter kind of complicated problems, you start with a representative simple case, right? You gain insight, then you generalize. Okay, at least for the one single input, the general single input system, single output system, that's called SISO, single input, single output system. We can, if it's not in the controllable canonical form, we can always do a similarity transformation to make it a controllable canonical form. And the design in the controllable canonical form domain and move back, right? It's like do a change of coordinates. By changing coordinates, your system can be described, if the system is controllable, okay? Can be always changed to a controllable canonical form, always. If it is controllable, you can do it. Then you design, then you go back. That's roughly what's going on. Okay, we learned that from the last lecture, similarity transformation. So your dynamic system will look different if you use different coordinate system, right? All this equivalent representation of the same dynamical system, they are related by this form. Here we ignore the C and D because it doesn't matter in this case. If you forgot this, then that's the last lecture, lecture 4, the last few slides. You remember the similarity transformation. You change variable. Suppose this is x, this is my x bar. They are related by this. This guy is non-singular. Okay. Then the relation between A bar and A is of this particular and form. Okay. Let's make the claim. Okay. Well, let's do a constructive way to construct such a transformation. So what I want is that I give system, this is it's not in controllable canonical, not in canonical form. Canonical form. Okay, A and B. I want to make it a canonical form, which I want to do in the form A bar and B bar, where A bar and B bar is in that canonical form. Okay, how to find this P? The question is that how use similarity trend we can have this. Okay, how to find this P matrix? Okay, that's the question we need to figure out. Okay, and we know the relation between the controllable canonical form of the MC and the controllability matrix in the relation between the similar transformed version of the two systems, MC and MC bar. Okay, they are related by MC bar equal to P inverse times MC. Okay, you can check the relation of the previous lecture note. I don't want to repeat that. Okay, so if we can find MC and MC bar, suppose, okay, if, that's a big if we can find MC bar, MC we know, right? This is given. Okay, this is given as B, A, B, all the way to A minus 1B. That's my controllability matrix. That's why we introduce controllability thing, okay? So A and AB are given. So you can compute MC. Are you with me? That's something we know to start with. Okay? And I know MC with MC bar is related by this P inverse. So if we can find MC bar, then P would be MC bar times MC inverse. Oh, sorry, that's wrong. P inverse is that. Okay, because MC is controllable. So sorry, the A and the B are controllable, so MC is non-singular. It won't be because we have a single input, it won't be a fat matrix. It's always a square matrix and a full rank. So it's invertible. So this P inverse is well defined, and the P is MC times MC bar inverse. Okay, now the question becomes, can we find this MC bar? Actually, yes. MC bar is defined as B bar, A, B bar, A bar, B bar, okay? Sorry, A bar n raised to power minus n minus 1. So B we know, B bar is always 0, 0, 0, 1. And A bar, all the first n minus 1 rows are fixed. The only thing matters, where is it? Yeah, the only thing matters is the last row, right? As long as we can figure out the last row, we're fine. The last row is the characteristic polynomial of A bar. Okay, so we rely on this fact. I'm not jumping steps, I'm just moving a little bit faster than maybe some of you may feel a little bit faster than you can take in the information. But all I need to find out is now is the last row of A bar. The last row of A bar only depends on the characteristic polynomial of A bar. Okay, and now I'm telling you the characteristic polynomial of A bar is the same as the characteristic polynomial of A. Why? A, right? A bar is P inverse AP. So they are similar to each other. They have the same set of eigenvalues. As I mentioned, eigenvalues determines the coefficients of the characteristic polynomial. Let me repeat. Eigenvalues, if eigenvalue is fixed, then characteristic polynomial is also fixed. So that's why these two characteristic polynomials are the same. This one is given. As we know A, right? We know A is given. Now, we don't know what A bar characteristic polynomial is, but because they are the same, so I can know it already. I also know it. Okay, that's the whole story. Okay, I think a little bit too much, so let's directly walk through the steps so you have a better sense. Okay. Let's say eigenvalue assignment procedure for general single input. Let's quickly walk through the steps and then go through an example, then everything will become clear. Okay. So step 1 is similarity transformation. We need to find P. All we need is find P. I go through several steps. Finding P is our goal. And to find P, we need, let's see how. To find P, let's say, we need MC bar. Okay? To find MC bar, we need A bar, because B bar we know. Are you with me? You have to walk through or think with me. And A bar has special form. I only need to know the last row of A bar. That's what we need. Okay? Last row of A bar is determined by characteristic polynomial of A bar, because that's a coefficient of characteristic polynomial. Okay, then this guy is the same, is equals to, because similarity transformation doesn't change characteristic polynomial. So this thing is known. Okay? If you go through the arrow, we start from some known A. We compute characteristic polynomial of A. Then we know A bar. Then we know the last row of A bar. Then we know A bar. Then we know MC bar. Then we know P. Do I remember this? No, I don't. Did I review this lecture before I come today? No, I didn't. But you also need to know what you need. Then you go backward reasoning. All you need is just a clear thinking, and then you know what you need, and what's given, you just reasoning through it, you'll find what you need. I don't want you to remember any formula, but I want you to become a clear thinker, that you know what you need and you can get what you need. Okay, all these steps are just repeating what the logic. So this is given. Start from the last thing. Okay, this is given, and I can write it out. This is given. Okay, can be computed. Then I know the relation between these two. I know the characteristic polynomial A bar. Okay, then I can write A bar, the last row, right? Then I can compute MC. Then I'm done. All right, I can find P. The catch here is I need to know MC bar and MC are invertible. Controllable. The system has to be controllable in order to arbitrarily assign eigenvalues. If not controllable, you can't. Okay, so that's the catch. We always assume we have a controllable system. Okay, now the second step is that we already learned the simple case, right? We can find K bar. So let me write. Okay, we have learned how to find K bar such that, because it is controllable form, I know it's just the last row, right? So such that eigenvalues of A bar, B bar equals, eigenvalues of A bar minus B bar, K bar is eigendesired. No matter what you desire, you just tell me, I can tell you K bar to achieve this. All right, now I need to come back. I need to compute what K is. You can check, well, I will just direct tell you the answer. You can easily find it out. Or you can check. Okay, check. Let's not check first. Okay, I think I have steps. We need, let's say, still try to emphasize what we need our goal. You still need to know, you always need to know what you are trying to find, what you're trying to do. We need eigenvalues A minus BK equal to eigendesired, right? This is our ultimate goal. Now what we designed is in the bar space, controllable canonical space, right? And we need to find this K. You can check. First of all, these two have the same set of eigenvalues. This guy and this guy have the same set of eigenvalues. If I design this K in this form, you can check directly because A bar minus B bar K bar equals P inverse A P. That's A bar, right? Minus B is P inverse B. K bar is K bar minus P inverse. So it's a K bar, K bar is K times P, right? So this is K times P. So overall you have P inverse times A minus BK P. So this term has the same eigenvalue of this because they are similarity transformation of each other. Okay, any questions? I think I feel tired. What about you? 太烧脑了是吧？每个 step 都 make sense， 但是感觉就是有点乱，是吧？所以我也不记得啊。但是至少你要 go through 这个 process， 这个 exercise。Okay, let's repeat again. You gave me A, B. It's not in controllable canonical form. I need to find P to make a controllable canonical form. The formula is here. The reasoning flow is this. Okay, this flow chart. All right, once you have P, then I learned design K in the controllable canonical form. I find K bar. Then I check, okay, if K define K bar P inverse, then A minus BK also have the same set of eigenvalues. So everything is linear algebra. Control is nothing but linear algebra applied, application of linear algebra in the context of control design, your purpose. Okay, as I mentioned, we need to do coding. So this will be hard in Python. I think it's less convenient than MATLAB, but we have to go through it. Okay, coding, this is A matrix, this is B. A is 3 by 3, B is 3 by 1. Okay, let's take a look of this. I think we have time. Let's do it together. Hold on. Let's see, this is our, I think that's the matrix, right? 2, 0, 4, is that right? Okay, these are the A, B matrix. Our desired eigenvalue is, 淑媛，你告诉我你想什么吧 ？eigenvalue， 你说几个 eigenvalue？ 3个 eigenvalue。随便嘛，随便 throw a number， 你不要想，想就没意思了 ，OK， 就随便想，你别整出个几万，好吧？2 ，OK， 得有 complex pair 还好一点嘛。4加10 4加3乘上 1j，OK，这 MATLAB 不 Python 好像是这样的，应该是，我记得好像是啊，这么去算，4减3，啊，这是 OK。All right, let's see whether it has error. Yeah, it's correct. That's eigenvalue, okay? That's Shu-Yuan's eigenvalue. Now let's see, can we achieve her goal? We start from...
finding P.
Yes, okay, great. Step 1, finding P. Finding P, okay? How to find P? Start what we have, right? Start from what we have. We have A. So we know A character is a polynomial, right? So how to find character is a polynomial? So it's called delta A is numpy dot poly A. That's it. Okay, let's see. It's let's check. Let's print delta A. It's 1, 2, it's just the coefficient of the polynomial, by the way. All right, that's what this means. Okay, MATLAB has just poly is the same thing. NumPy dot poly is the same thing like MATLAB poly. I would say slightly different, but serve roughly the same purpose. I somehow n is 3. Okay, that's our dimension. Now I can construct my A bar and B bar. Let's first do the simple one. B bar, okay? B bar is, let's say numpy.mat. I like to use mat because otherwise I need to use other ugly location or use dot product. That's just everything is mat matrix is fine. So mat numpy.zeros n by 1, 3 by 1. No, is that right? And the last row, how to refer to the last element? -1, okay? -1, 0. Because MATLAB start from 0. So -1 is the last row, first column, because you only have one column, equal to 1. Okay? If you print this B bar, 0, 0, 1, okay? You can type in this, but I'm just do a little bit more, I would say less hard coding. B bar is done. What about A bar? numpy.mat, the numpy.zeros. Zeros give you array. I don't like array structure. I mean, sometimes it's n by n, right? That's 3 by 3 matrix. I need to change the last row. What's the last row? Let's do by hand this time. I don't think, no, not only last row, sorry. The first row, the second element is 1, right? So the first row is, second element is this is 1. And the second row, third element, which is 2, is 1, okay? And A bar, the last row. Last row is the third, equal to the delta, that is the coefficient here, right? So let's not type in, because let's say this is I think it will be negative delta A from the last, the first one is the last element of delta, okay? So it's last one is -1, okay? Or you can use 2, it's fine. The index is -1 to the 0, semicolon, comma, and the -1. The last -1 is a step, okay? You start backward in time, right? It's, yeah, that's what I mean. Okay, you can print delta A. What we want is 16, -8, 2, this way, right? And I think this will give us the answer. We can try.
No, I think
you can see A bar is what we want. Okay. This means start from the last one. Okay. To the second last. Okay. Backward in time. 是怎么说啊？从最后一个开始 ，OK， 往前数，对吧？一直到0吗？不是，这不是每一次嘛，递减嘛，就是 index 从从2、1、0，对吧？然后呢，因为 Python 它不 include 这个 ，OK， 它是你要是往前数就大于它 ，OK， 从前往后数就是小于它，从后往前数就是大于它，就比它再多一个，就提前一个 ，OK。所以就是就没有包括第一个项目，就是云天 vary 我们是不会包括第一个项目没有 ，OK， 这是 right。We don't have to do this. By the way. All right. Now let's say MC is np.block. What? B. A times B. A square times B. Okay, that's my controllability matrix. And MC bar is np.block. What is it? B bar, A bar times B bar, A bar squared times B bar. I think I missed one bracket. Okay, so that's our two control. Okay, that's it. P is MC times, let's say LA dot inverse MC bar. Okay, I can use MC bar inverse. That's fine, but I have to use this. I think I'm done. Okay. If no error, I think I'm done, but I need to check, all right? Is this, how do we check? Let's say print P inverse times A times P should give me my A bar, right? So it's a P inverse. Now I use this. This is inverse, okay? Times A times P. That should be my A bar, and the P inverse times B should be my B bar. Okay, let's print these two things. Is this right? Yeah. Just there. 0, okay, 0, 1, 0. You see the negative 15 is numerical epsilon, the machine epsilon. 0, 0, 1. 负16, 8和负2. Okay, that's what we want. 0, 0, 1. Okay. If you use, this is different, by the way. So if you use LA dot inverse, I will be a little bit better, I think. P. LA dot inverse P. I think that's numerically better. Somehow you see less machine epsilon, but essentially they're the same. Okay. We finished this one. Now we need to do what? Delta, I need to say delta A desired. Delta A desired is my, let me use your 2 minutes, okay? I desired. Poly has two things, okay? If you give me the roots, I will tell you the coefficients. This is my desired characteristic polynomial coefficient. And the K bar should be equal to np.mat delta A desired. I'm to use my magic indexing rule, okay? -1 minus delta A -1 to 0, -1. Okay, then I can LA dot I evaluate A bar minus B bar times K bar. Haha, delta desired is wrong. Delta A desired, sorry. It's 2. It's Su Yuan's. Okay, that's in the bar space. We need to move back. I will skip this part. I will tap the rest and send it to you through website. Okay, that's it for today. Okay, last time we learned how to design controls, right? I hope you understand the control design is nothing but placing eigenvalues of your closed loop system, right? That's the key message I want you to understand. Okay? And we learned 2 different cases. It's always like any kind of a complex problem, we always start from the simplest problem, right? Like when we analyze stability, we start with diagonal matrix. Now we start with so-called controllable canonical form of system dynamics, which is of this form. And the key property I want you to really remember is that the last row matters, right? The last row defines the characteristic polynomial 特征多项式 of this matrix, okay? And given this matrix of this form, you can immediately write down the characteristic polynomial. And you also need to know the polynomial and the roots of the polynomial are, the polynomial coefficients determines the roots. And the roots also determines the characteristic polynomial coefficients. Okay, if I gave you the coefficient, you already know the roots. If I gave you the roots, you should know, you multiply them out, you should know the characteristic polynomial coefficients. So if the given matrix, that's the eigenvalue does not satisfy, it's not what you desired, then you need to change, right? And the controllable canonical form has a property that you can directly, the control gain, although this gain matrix here is very special. It's a vector, it's a row vector. It's 1 by n. And you can directly modify the last row of your matrix so that this will be your closed loop A matrix, right? So you can arbitrarily determine or you can arbitrarily determine the last row so that you can arbitrarily determine the eigenvalues of this closed loop A matrix, all right? So I hope that's fine. I will give you examples. Later, when we have a general single input, single output system, and we need to do a change of coordinate, a key message here you need to remember is all the controllable system can be transformed into a controllable canonical form by similarity transformation, okay, or by change of coordinate, okay? So you can move back and forth between your original system and its controllable canonical form, okay? And we learned several steps, right? Step 1, find P. Step 2, find K in the controllable canonical form. And step 3, and move it back. And then we went through an example in Python, okay? In the Python, we didn't call any built-in functions. We just did everything by ourselves. I think we almost done last time with Python, right? So that's the matrix we were trying to control. This is the open loop, A and B, right? Then I asked the student, what's her name again? Su Yuan. This is Su Yuan eigenvalues, right? She did, I think it's yours, right? You told me you want 2, I don't know why you want this, okay? 2 and 4 minus plus 3j, okay? That's your eigenvalues. And we went through the step 1, 2, 3, 4. We find out k bar, and we move back to k. And I think let's run that again. Okay, so the print eigenvalue evolves. A minus bk is 2 And it's just what we want, okay? So I will upload this to the GitHub link that you can download. All right, I also want to mention one thing, is that MATLAB has built-in function to do pole placement. But Python does not have a good support on that, but you still can, for simple case, you can use the signal package, and the signals place poles, okay? A, B, eigendesired, I can find the gain matrix, this is called feedback gain, and and A minus B times the feedback dot gain matrix will be Suyuan's eigenvalues again. All right, this you can directly call it, and we compute by ourselves here, right? And you can compare the K here with our K. If we want to print, let's say, print our K, and the Python, the signal class place return the K. That's gain matrix, gain matrix. These are the two gains, all right? They're exactly the same. All right, I'm not saying, the place function actually can deal with more general cases than what we can do now, but in single input, single output case, I think you almost know exactly what's happening, all right? More general case, it will be pretty nasty. I wouldn't discuss them, but I want to mention that a little bit so that you can roughly see the flavor. Okay, so far we have learned, hold on. So far, well, where is my, okay, so far we have learned the design for single input, single output. That's the restriction. I'm not sure whether you realize it or not. Single input, single output. Can anyone tell me if it is not single input, single output, can we really find this P in this way?
No, we can't, because
MC bar will be a fat matrix. All right, it's non-trivial to see how you can invert it directly, okay? But you know this fat matrix at least have rank n. You can at least find n independent columns, right? You can use that independent column to convert it. Actually, that's possible. But I'm not going through that. I'm just giving you some example. You can see the flavor how you can design this by hand. But typically, you would do that through online kind of a Python package like a place. Let's talk about example. Let's say one example is suppose I have a matrix. Let's say it's my favorite matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. My favorite 3 letter is verify yourself, right? A matrix is typical 1, 2, 3, 4, 1, 2, 3. I mean, it's just for simplicity. And a B, let's call it 1, 0, 2. It's a 3-dimensional single input system, okay? So it's single input. So we have learned how to design a K. Let's call this K. In this case, what's the dimension of K? Let's call it K1, K2, K3, okay? I can find this row vector or 1×3 matrix, a gain matrix, such that A minus BK, the eigenvalue equal to eigendesired. So use eigenvalue, right? That's fine. We know how to do this now because it's a single input. All right. Now the question is that, let me give you an example. Suppose, let's example 1. Suppose my A is the same. It's this guy, move here. All right, I don't want to copy. It's my favorite matrix. B is 1, 0, 2, 1, 1, 0. How many input I have? How many inputs I have? 2, right? You should tell me, don't. I'm not taking picture, right? 2, okay? 2. But based on what we have find in one input case, can you tell me a solution of 2? So in other words, we don't know how to design this. Following our previous steps, this case, we cannot handle, right? So can you find K? In this case, what's the dimension of K? 2 by 3, right? So it will be K1, sorry, I cannot use this K1, okay? So it's something we need to find. Because what? U equal to negative Kx, right? U is 2 dimension, K times X has to be 2 dimension. So that's why K is 2 by 3 matrix, all right? Can you find this so that our eigenvalue is X desired? Yes, we can. I would just say, for example, we can let, I would say there is multiple solutions, this K, okay? This is, I would say the solution is not unique. It's not unique. All right? And for example, we can choose, we can pick, let's call it pick. K equal to K1, K2, K3. That's my K here, okay? These are the same K. Now, the second row, I'm just putting 0. What do I mean is that I only use my first input, and second input, I set it to 0. Because no matter what state I multiply with, only the first U1 equal to this K1 times X1, K2, X2, K3, X2, and the U2 will be all 0, all right? So in this case, I can say eigenvalues A minus, to distinguish our notation, sorry, I will just use this as tilde. Okay, they're not same. And this is my tilde K, all right, tilde K. So this is A tilde, B tilde, K tilde equal to eigenvalues of A minus BK. Can you see this? Okay, you can verify that. Essentially, it's equivalent saying you only have one input because you didn't use at all the second input. Of course, by using the second input, you would be able to stabilize or make your system stable in a more elegant way because you have more freedom to design, right? So the first input will not as stressed as it was before because you have a second input to help you. It's like 2 people do the same project. Now the second people, in this case, I know Yuntian can do the project. So the second one, he doesn't need to do anything. It's the same thing, right? If 2 can share, then it will be better. But in terms of solvability, this is possible. And I want to also mention another one case. For example, A tilde is the same. Now let me not call tilde anymore. It's called a hat, okay? B hat, this different matrices. I would say this is 1, 0, 1, 0, 0, 1. Okay, this is 2 input. It's different from B tilde. Okay, now I directly tell you that we can let can you see that the first column of B hat plus the second column of B hat equal to 102, right? You see what I mean? Okay. So we can pick, or we can let K hat equal to, I want the two to sum together to get to be the same as the single input. So we'll repeat this. Okay, and I think that will give me the answer as well. In this case, I will say A hat minus B hat K hat, the eigenvalue should equal to X desired as well. Huh? You don't understand? Okay. Let's verify yourself. No. Let me verify for you, okay? You don't understand. Let's say, let's start from the basics, okay? Now I have this, let's check. First of all, let's check, okay? So A hat minus B hat. B hat is, let's just write it down, right? So it's 101001 times K hat. K hat is K1, K2, K3, K1, K2, K3. All right, if you don't understand, just plug in and verify by definition. And I know this A hat is A, right? A hat is A. Is that true? These two are the same. Minus, can you just multiply? What is it? This is a K1. K2, K3, 0, 0, 2 K1, what? 2 K2, 2 K3. Okay. All right. If you do this, A minus B K. This is A, right? So A minus B is 102 times K1, K2, K3. You find it out. It's the same. Isn't it? Okay, so the eigenvalue will be the same as well. Okay, so you can plug in. Oh, I skipped steps, but I shouldn't, maybe. All right. It's just plug in, they're the same, right? So essentially, I have two inputs. I treat it as one. Okay. So as long as I can find one column, a single input case that makes the system stable, then I'm fine. All right. If I have more freedom, I can decide not to use it, or I use it in a smart way. But we didn't learn how to do it in this class. But at least I think you can know. Have more input is not the problem become harder. The problem may become easier. Any single column may work. But if you want to design a better or improved version of the control gain, that becomes a little bit harder. Okay? But just solve the problem. Place the eigenvalue is not hard. Okay? That's my comment. I don't test you on this, but at least I think you can roughly see how this may work. So in general case, it's quite involved. They usually use numerical tools. That's place function we just use. You can give them arbitrary number input and output. Or we are going to learn LQR, linear quadratic regulator. Hopefully I have time to touch that later on in this class, and that can deal with arbitrary things. LQR becomes more and more popular in robotics nowadays. Before, it was just maybe 10 years back before very few robotics people use it. Now almost everyone start using it. LQR and the MPC, they are strongly related. We will touch both of them later in this class. Okay? All right, let's move to the next topic. So Shuyu tells us her desired eigenvalues. I'm not sure whether you agree or not. What was the eigenvalue? Do you think it's good or bad?
Not converged, I think.
The eigenvalue is even not converged. Okay. Where is it? Oh, okay, I don't need to look for that. So her eigenvalue was 2, 3 plus minus 4j. The 2j or 4j? 4j, okay? It's unstable eigenvalues. You know it's not good to have for a closed loop system, all right? But what is a good eigenvalue? Do you know it? As we mentioned before, the smaller, for discrete time system, the smaller the eigenvalue is, the better, the faster it converts, because it's exponential, okay? So can I make it as small as possible?
Yes.
Why not? So how should I put it? If you ask me, I think eigenvalue, I can pick 0.5. Why not put 0.1 or 0.01? Is there any trade-off that prevent you from selecting overly small eigenvalues?
The magnitude of input, maybe.
Yeah, exactly. So I think you learn, at least you learn much more about this in your undergraduate. This is also undergraduate. So classical control, right? 现代控制工程，不，控制工程或者是导论什么的，对吧？自动化原理。But that's you learn in the continuous time. Let's briefly recall. So if you have a system in continuous time and discrete time, they are similar. It's just a change of from S domain to Z domain. If you have a system, you would like in continuous time, you would like your poles to be in the open left half plane, right? In order for it to be stable. Did you do the lag compensator or lag compensator and the PID, root locus, body plot? You learned this, right? You forgot, I agree, but you learned. Did you or did you not?
Yes, the locus.
Root locus, okay. 根轨迹、波特图，对吧？这些东西。How to select poles? In that case, you need to design your compensator, they call compensator, so that your closed loop roots, poles, located in the open left half plane, and you need to pick those poles, right? How do you pick those poles? Exactly the same question. If you ask me, those are engineering details, okay? Choosing what poles you want the system to operate at, there are some general guidelines, but there's no theory. To me, it's art, okay? But the key message I think everyone should know, if you forgot, you should somehow recall it or learn it now, is that a rule of thumb is that you typically think about your system as a second order system. Do you remember second order system? This is your, everything was defined, okay, typically, depending on what textbook, no matter what textbook you use, they will start talking about system performance, transient behaviors in terms of second order system, right, of this form. Okay, so in that case, this guy, omega n, is called natural frequency. This is called damping ratio. So you will have some overly damped system, 欠阻尼, 过阻尼, right? Under damped system, critically damped system. So if you have a under damped system, you will start have oscillations. Okay? All these relate to how fast the system will respond to your input signal. I'm not sure how much you remember that, but that's a key. Why we study second order system? It's simple. Yes, and you have a roughly, I'll say, you can roughly see how it works. Okay, you can play with it very easily. What if your system is not second order, it's fourth order, fifth order?
It can be divided into
you have so-called the dominant poles. Do you remember dominant 怎么翻译来着？支配性的 ，OK。你是字典翻译还是教科书的翻译？字典。Those are, you can think about them if your system are not dominant poles. It's not second order. You treat them as if they're second order. All the other poles, if you have the chance to design your controller, you should move them to further away on this plane, right? So that's your system will be approximately second order. Can you see that? Of course, if your other pose is here, then the approximation is bad. They're too close. If they're further away, like very far away, then the approximation is really, really good. The reason is what?
They will die out quickly in the mortar.
Exactly, that's a approximation. No, sorry. It's, if you look at your transfer function, let's say that, okay? You have your S minus P1, that's your first pole, second pole, third pole, dot, dot, dot. Let's say this is a numerator, I don't care for now. All right, and pole could be complex, right? So let's say Pi is sigma I minus plus J omega I. Okay, that could be complex. So if, let's say if sigma 3 is much less than sigma 2 and sigma 1, sigma 2 and sigma 1 are conjugates, they're dominant poles, suppose, okay? Then the response part will have one piece of component that's related to this pole, which is of the form of e to the sigma 3 plus minus j omega 3 times t, right? So this exponent is much smaller than that thing, so that it converts much, much faster to 0. It's exponential difference, okay? So differ a little bit can make it convert to 0 much, much faster. So you can typically approximate a system as a dominant pair of poles, okay? So that's why we focus on second order system. You should go back to your textbook. I think all of them should talk about this, but you may not pay much attention to this. Okay, so we can focus on second order system. That's all the reasons. Because we have the freedom to place poles, both in the frequency domain, like in your control engineering class, and in this class, we place eigenvalues, the same thing as poles. So we can design the pole to be further away from our dominant poles, right? So that's our design choice. Okay, let's talk a little bit more about this. I think you should learn this before. Let's give a little bit more details. For underdamped case, that's our, actually, when you have dominant poles, you typically consider the underdamped case. Not because you want oscillation, it's because it will be faster. If it's overly damped, it converts typically much slower. It's very, very slow, right? You would like to sacrifice a little bit overshoot, but it can convert faster. Okay, that's a trade-off. I will explain that later in the next slide. Okay, the pole is of this form. Okay, if you just factor this denominator, you will find out this the pole format is negative zeta. This is called zeta. Okay, zeta omega n natural frequency plus minus j omega n 1 minus zeta squared. Okay, so that pole, two poles P1, P2. This is the real part. Okay, and there's the angle of the pole. And this angle, if you like to see it, is if you think about the cosine theta is what? Cosine theta is this guy, which is omega n squared. Anyway, that's zeta omega n. Sorry, I don't need to take squared. So that's the length. This is zeta omega n divided by the length of this thing, right? So which is zeta omega n squared plus this guy squared, which will be omega n squared times 1 minus zeta squared. Okay, you'll find it out that's zeta. So theta is the inverse cosine of zeta. So the damping ratio tells you typically how big this theta is. All right? Did you finish? Now let's look at how does this relate to the system response. I think all of you have heard about those response metric. This is called time domain performance index. Okay. One thing you must have heard of is steady state error, 稳态误差，对吧? This has nothing to do with transient. It's really about steady state. Let's not worry about this here. But things related to transient is the following: cycling time, peak time, and percent overshoot. All of this cycling time and the peak time is about response speed, how fast the system responds to your command. And the percent overshoot is just some oscillation that you try to avoid. Okay, but there are formulas. The cycling time, I think those are, I'm not sure whether it's exact or not. It should be approximately, there's some approximation involved. Okay, so roughly how do they relate to the poles? It's those relations. You can derive them. I think it's very easy. I assume you have seen this before. Okay, so let's discuss how to we place our poles. First of all, if you just consider this second order system, if poles moves up, moves to the left, what will happen? This will be means zeta omega n becomes bigger, right? So the system is typically referred to as being more stable, okay, to the left. So you can see this increase, that means cycling time decrease, right? So that means it converts faster. So the cycling time decrease. Do you want this or not?
Yes.
You want cycling time to be small, right? You want the percent overshoot to be small. You want peak time to be small. You want everything here, the metric, to be small, okay? Let's say, let's fix this, the real part. Let's increase the imaginary part so that the pose moves up, okay? If the pose moves up, that means we have larger this guy, okay? Larger this guy means smaller TP, okay? The more complex, okay, the less real. I mean, you're further away from the real axis. This is the real axis, right? You moves up. Once you go to infinity, it's almost like you're in the imaginary axis. The peak time will be very, very soon. So the first time you hit the peak, this is called peak time. All right? But this case have large theta, okay? And this leads to large percent overshoot. That's the trade-off. Your peak time could be small, but you have a big overshoot. Okay, the faster you want your peak time to occur, the bigger the percent overshoot is. If you fixed, of course, if you fix your real part, okay? You have any question? What's your question? Larger percent overshoot. Larger percent overshoot. That means percent overshoot, okay? So you can verify the relation because those things are all monotone, okay? And the smaller, so then why not smaller theta? Smaller theta will have smaller percent overshoot, but it will be bigger TP. Okay? Your response is more sluggish. Okay? So the key is that, okay, so that's all about fixing one real or imaginary part and moves the other one. The catch here is that the key, I would say, constraint here is that implicit constraint, we didn't say it, is that we can't smaller PO, samer, 不是 samer, smaller, okay? Smaller percent overshoot. You should learn this before, right? Of course, you're playing with it for almost one semester. Otherwise, how did you design your first controller? Leak compensator, lag compensator, how did you design it? Where did you place your pole? Whatever your instructor told you, 告诉你放在哪儿就放哪儿是吗？It's your design choice, okay? The key constraint that we didn't explicitly mention is we can't move poles too much to the left. Like Yuntian mentioned, okay? So, of course, one thing is always better is that I can keep moving this to the left. So the conversion will be faster, right? So nothing else. There's no other kind of trade-offs I need to make compromise with, okay? But the problem is that here will be typically that means that results in large control actions. Okay. So you may want your motor to be really, really strong in order to support your control or the desired control action, right? So typically we don't have those unlimited. We have very kind of limited budget about how big your control action could be. So that's an implicit trade-off here. It's not very clear, right? Oh. Anyway, I will upload this soon, so let's move forward. Okay, so that's the recall for continuous time. Your control engineering class. In this class, we deal with discrete time. Actually, in most engineering system design, you need discrete time. You have sampling time. How to move from discrete time to continuous time to discrete time? Z transform. Okay, you have Z transform. I know it is a discrete time version of a Laplace transform. That I think we mentioned before. And the poles of the Z transfer function is Z1, Z2. This guy, the poles, these are the poles in the continuous time, which is called P1, P2. Okay, how to change them? I know that Zi or Z1 e to the P1t and the Z2 equal to e to the P2 of t, right? As I mentioned, the relation Z is e to the st. We derive it early in this class. I think you should learn it in your signal system or control engineering, but we rederive it for you in lecture note 2, right? Z is, the Z and S relation is that. So you plug in the poles for S, you got the poles for Z. Okay, let's have a kind of simple or the simplest design exercise. Okay, suppose we want the cycling time. I gave you a continuous time system. Okay, continuous time to start with. I want the cycling time to be less than 5 seconds. Percent overshoot 35%. Okay, it's not too hard. So what are the poles satisfy this requirement? There are a lot. Okay, we can pick one. So the requirement, we can just translate them to TS is 4 divided by zeta omega n less than 5. Right? Let me finish this part. 100% over to 100 negative zeta pi divided by square root zeta squared less than 35. That's percent overshoot formula. Okay? I have two inequalities. Actually, I have infinite number solutions. But I can simplify these inequalities like a zeta omega n should be bigger or equal to 0.8. That's easy to calculate, right? And zeta, in this case, this is just a nonlinear function of zeta. It's actually monotone. Okay, I wouldn't want to do that. I think you find this is, so this inequality just means this. Roughly, okay, I think I did some numerical approximation. So we can pick arbitrary things that satisfy these two conditions. So we can choose zeta equal to 0.5 and zeta omega equal to 1. Okay, this tells us the zeta satisfies this, right? I can have some buffer. I don't want to pick zeta exactly this, right? I want to be a little bit bigger than the minimum requirement. Okay, so omega n equal to 2 in this case. So then my desired eigenvalues or poles is not SUS eigenvalue anymore. It's -1 plus minus j square root 3 in this case. If you just plug in the formula for the poles, that's what you get. And if the sampling time is t equal to, let's call it 3. That's my sampling time. I don't think we have such big sampling time typically. Let's do that smaller, sorry. Let's say 0.30 milliseconds is our sampling time. Then my desired, the z-domain pose is e to the -1 plus minus square root of 3j times 2. Oh, sorry, not 2. Times t is 0 to 3. That's our discrete time. These are pole locations that I need to place or assign. No, sorry, place the closed loop system. All right, I think we will go through later go through several examples. I think this will become very clear later on. All right, let's take a break. Okay. So now we have completed eigenvalue assignment, eigen assignment problem for control design. The assumption we make is, so far, is the state feedback. Okay. So our controller is of the form. Our controller is of the form k times x, right? Wow, so many derivations. So that's the feedback control part. I think, wow, we derive so many things. So the controller so far is k times x. That's our assumption. Here's our assumption here. All right. And in reality, you typically don't have access to the full state. Most of the time, I think in typical engineering case, oftentimes I would say you don't have access to the full state. So the control design method we learned so far, in that case, cannot be applied, right? You need to be, so your controller so far, our controller is what? So far the full state, let's say full state, feedback. So the controller is of the form that this is our control law, that's control law. The input need to be state and output is U. Okay? That's our controller, but output feedback. Output is something you can measure, okay? It's available to you. How do I move this? Output feedback is that this is why the controller depends only on the system output. So why not directly measure all the state? Two cases, okay? Sometimes we cannot, right? It's just like the full state of your any robot, at least the base, is the X, Y, Z, and the raw pitch roll, okay? But if you have an IMU, inertial measurement unit, they only give you the raw measurement is only the accelerations and also the angular velocities. Okay. The other thing you have to estimate. I don't think you can directly measure them. In other case, you have a lot of state. You may not want to use all the sensors because it costs money. Okay. If you place a few sensors, so that's enough for you to guess or estimate or observe the entire state, then you don't have to have a lot of sensors. Okay? Sometimes it saves the cost. Two cases, either case, you don't have access to the full state. All right? So if we don't have access to the full state, but we only learn the state feedback control, how do we do it? We divide the design process into two parts, right? The first part is that we use the system input output to measure, so to estimate the controller, the state. So this is my output. I pass through that with a observer, the so-called observer. An observer gave me an estimate, I call it hat. An estimate of the state. It's not the true state, all right? And then you use that as your control. Let's call it, this is the state feedback control. Then you go to this U of K. So the whole thing here will be this guy, right? You divide it two parts. You don't have state, you estimate or observe state first. And second part, you treat as if the estimated state is the true state. Then you use our learned feedback control strategy to design your controller. Is that clear? You don't know how to do this observer yet. Okay, how do we estimate the state based on the output and also based on input, by the way? You have to pass through that observer, your input as well. Okay, now it's observer. We were going to learn two types of observer. In this lecture, we're going to learn Luenberger observer. That's the most classical deterministic system observer for linear system. And the entire next month or two, we're going to learn common filter. Common filter is nothing but estimate state. You can think about it as an observer of a stochastic system. There's some random noise involved. Okay? Common filter does similar things. Based on measurement, estimate your state. Okay, so let's first look at the deterministic case, the Luenberger observer. So what's given to us is I have ABCD matrix, that's my system model. You know that, all right? That's system model. However, I don't have access to the full state. I only have access to Y, maybe have much less dimension than the state, okay? And I also know my U. U is something I send to the system, okay? So the question is that, can we generate, estimate? The key word here is this, okay? Iteratively, okay? According to some known system dynamics so that my estimate will eventually converge to the true state, okay? If you want to determine your true state, as we mentioned before, that's related to observability. Observability, how to define observability?
For any given UK and X, UN and X, we can uniquely slow the X there.
Almost right. But in math, there's no almost right. There's only right or wrong. 99% right is wrong, okay, for mathematics. Pretty good. So not for any UK, okay, so for any initial state, all right? You can use a finite number of observations, Y, to determine that initial state uniquely. Okay, if that's possible, then you can compute the initial state and then use your model to predict or to calculate what's the state at this moment. That's one way to do it. That's very dumb, not very smart way, okay? But that tells you the system is solvable, okay? You can definitely get the true state. And Luenberger observer is an iterative way to find gradually of the system state. Okay, let's look at this structure. Okay, so let's just look at this. Is nothing but Luenberger observer, as simple as this. One line of code, if you like. Can you tell me what's going on? This guy is not true state, it's your estimate. At time k, right? Xk hat. I don't know whether it's right or wrong. It's maybe that it should be different from xk. Okay? So the update is of the following form. Let's say, let's first look at the simplest case. So if xk hat, my current estimate, is exactly xk, what will happen? So you're lucky at this time, your guess is exactly what the system state is. Then the system update, how you update? Then I can see that this guy will be Cxk will be Cx plus du. There will be just y, right? I call this guy a correction term. It's like an error, right? If your estimate is right, this error will be 0. If your estimate is wrong, the error is that according to this estimate, you expect to see Cxk hat plus duk, right? And you minus yk is somehow a surprise or error. And based on this error, you have a gain matrix to multiply to update it. Let's say if the system is right, then the correction term is 0. Can you see that? Of course, because yk is just equal to Cxk plus duk. This will be 0. So I will say xk plus 1 will also equal to xk hat, x hat k plus 1. Is that true? So whenever you are right, you will be right forever, right? So next time you will be correct, next time will be correct. Are you with me? Okay. Now the most of the time, I don't think we are lucky enough. So this guess will be different. Is that true? The guess will be different. So the estimate will be then, this formula is just modify the estimate by multiplying the gain matrix. This L is a gain matrix. L with the error. The error term is y minus y hat k, okay? Let's define this y hat k is cx k hat plus d of uk. So based on your estimate, your estimated output will be yk hat. If yk hat is different from what you see, then there will be error. Based on the error, how big the error is, you make some connections. And this L is the gain for the correction. So if I do a for loop, on this, each time I will have what? I'll have one xk hat will be my output. Okay, it's my estimate. This xk hat will change over time. What I want is that this xk hat eventually converges to xk without hat. So this formula is the so-called Luenberger observer, very famous or very basic and famous observer. This is simple, right? No? Why they propose this form? Then you may ask that. It doesn't matter. They propose and they prove it. You can propose your own form. Xiaohan, can you propose a form? Xiaohan observer. I can propose one, right? I can say, I don't want this, I want 2 times L plus this, right? Works. Xiaohan observer, that's fine. The key is that you propose something and you prove it solved your problem. And then people give a name. That's it. Don't think about them as nothing can be changed. It's just, you want to solve this, right? And the key is the next page. You can propose this form. Next is that, does this really solve our problem? What do we want? We want, by doing this update continuously or iteratively, we want xk hat convert to xk. Okay, now let's start to see whether it convert to xk or not. You should be able to do analysis like this now, all right? Let's define, as I mentioned before, if you want something convert to something, you want the error convert to 0. So 0 is always our desired equilibrium. You want something converts to it, okay? So let's say my error is x hat minus xk hat. Sorry, xk minus xk hat is also, the error is also in Rn. Okay, so now let's say A is our definition n by n. C, typically I call it what? P by n, right? P by n. Then I'm asking you what's the dimension of this L? L need to be multiplied by something, a vector in P dimension. But the result should be in n dimension. So L should be n by P, right? L is n by P. Okay, so do not worry about this for now. Let's just derive it. So you want to see how error evolve over time. That's what you want. Okay, so let's say k plus 1, that's the dynamics, the error dynamics, how error evolve over time. So error is not a static relation, it's a dynamic. So ak plus 1 equals to what? By definition, it's nothing but xk plus 1 minus xk hat plus 1, right? That's by definition. But what do you really want? is how does error at k plus 1 relate to error at k. That's what you want to see, right? So you need to move back one step to see k. So xk plus 1, I know how it relates to xk. So it's axk plus b of uk, right? Minus x hat k plus 1. So what is it? That's our design. That's the observer. So we can use Luenberger observer or Xiaohan observer. Let's pick Luenberg for now. Okay? We can analyze the other one as well. So Luenberger observer is what? It's a xk hat plus b uk. Plus or minus? Plus L hold on, sorry. I want to do this. No. What is it? Okay, let me scroll down. Where is it? Here. Okay, L times yk minus cxk hat minus d of uk. Okay, that's our Luenberg observer. Can you see something can be cancelled? This guy and this guy. That's by design. Of course, you need to pick things smart so to cancel things out. What else? Let's say we also know yk note. Yk is cxk plus d of uk, right? That's our yk. Yk is the true state induced output. So this guy equal to will be a. I think this guy also cancel out with this, right? If you express this out, this cancel with this duk. Are you with me? So what's left? A times this, right? So A times xk minus xk hat. All the u related terms are gone, okay? So what's remaining is only this term. So it's minus L times, if you write this yk out, is c xk minus x hat of k. Everything related to u has been cancelled out by our design, right? So overall, we have, this is nothing but error of k. So what we have is a minus lc times error of k. So if I want to write a complete system dynamics, I will say ek plus 1 equal to a minus lc times ek. This is a linear system. It's a linear dynamic system, is that right? So then I can ask, can anyone tell me when the error will converge to 0? Eigenvalues of A minus LC in the unit circle. Okay? So we learn the stability. You see, we transform this observer design problem to a stability problem. So that's the underlying nature of the problem, is nothing but stability of a linear system. Okay. So now inside this, what is our design parameter? So these two guys are known, right? These two guys are known. But the IO we don't know. That's our gain matrix. You can try, right? You can tune different gains to see when the eigenvalues will be less than 1. right? The magnitude is less than 1. That's tuning. But we also learned how to place eigenvalues using pole play or eigenvalue assignment. But this is different. What we have learned. Anyway, by the way, let's move to the next slide, okay? So finding SUSL, so it's observer design, sounds pretty fancy, right? Observer design for linear system is nothing but find a gain matrix L such that the aerodynamics has desired eigenvalues. It's like a pole placement or eigenvalue assignment for this system. Let me repeat. Observer design is nothing but you try to find a matrix L such that NA minus LC has desired eigenvalues. You want how fast your observer, your estimated state converts to the true state. That's what you really want. Okay, you want that to convert fast. So now that's the fundamental nature of what you're doing. You can tune it, right? You can try and error. But fundamentally what you're doing is trying to find L such that A minus LC has desired eigenvalues. Okay. How did we learn previously these psi eigenvalues? We start from controllable canonical form, we do chains of transformations, right, and move back and forth. We can do that again for this thing. There's so-called observable canonical form, okay? But we don't have to do it because by just change of notation a little bit, what we have learned before immediately used here. This is so-called duality theory or theorem. Okay, let me state that AC observer design only involve A and C here, right? Because what? It's not we assume there's no B. There's B but canceled out. It doesn't matter. No matter what B it is, it doesn't matter. It's just like a controllable case. No matter what C is, it doesn't matter. So now is AC is called observable. First of all, we need to solve ability problem. Okay, AC observable if and only if A transpose, C transpose is controllable. I'm not sure whether that sounds confusing or not. What do I mean by A transpose, C transpose controllable? We say something, don't attach your understanding to the notation people use. You should understand the meaning, right? Whenever I say some matrix, let's change the notation, F and H. Whenever I say A, F, and H is controllable, what I mean is that if I treat F as a system A matrix, H treated as a system B matrix, then this system is controllable. Or in other words, the controllability matrix MC is H, FH, F squared H is a full rank. You see what I mean? So this is controllable by definition. What we mean is really this system. This system. Okay, it's just we didn't write it out. It just means will be my system A matrix, this is system B matrix. All right? So when we say A transpose, C transpose is controllable, all we mean is that C transpose is our new A matrix. Sorry, A transpose is our new A matrix. C transpose is our new. It's like this system. K plus 1 equal to A transpose xk plus C transpose uk. It's a linear system, right? This will be our A matrix. This will be our B matrix. Okay. So this duality theorem tells us the following. Let's say, let me briefly argue through this case. All right, AC observable. We have learned, you may forget. I will quiz you next time on this maybe. Today I forgot to add this question. AC observable, what's the meaning? Okay, the test, okay, let's say not definition means, of course, the system you can use y and u to estimate or uniquely determine initial state. And the test is rank of MO is n. Observability matrix is n, where this MO is, I think all of you like test because that you can memorize some formula, then you can solve the problem. Okay, how did we derive this? Based on definition, use the solution, system solution released equations, then we find it out. Okay, that's nothing fancy. That's MO is this, all right? So I'm going to claim this guy equal to n is equivalent to, say, rank of MO transpose equal to n. Do you agree?
Yeah.
Rank of n, A equal to rank of A transpose. Number of independent columns equal to number of independent rows. That's what we reviewed at the beginning of this class. Okay, so now we know MO transpose, in this case is what? Just take transpose. A tall matrix become fat matrix. I wouldn't call it fat, okay, so it's a wide matrix, all right? Wide matrix. Tall matrix become a wide matrix. So this will be C transpose. The first block. Okay, second block is A transpose C transpose. All the way to A n minus 1 transpose C transpose. And these two can be reversed. Okay, so it's A transpose n minus 1 C transpose, the same. What you can claim? Then I can say as if this is my B, this is my A, B, right? So that's similar to that. So I can claim, so that's similar to say A transpose, C transpose is controllable. AC observable equivalent to A transpose, C transpose controllable. We prove it. Okay, it does not, I mean, if you don't understand it, that's fine. But what this entails, I want you to remember. Controllable, we learned, right? If a system is controllable, we can arbitrarily place eigenvalues in the form of A minus BK. We know how to do it now, right? In other words, if AC observable, then somehow we know how to place pose for A transpose, C transpose. Okay, so that's the consequence, duality theorem. If system AC is observable, we can use feedback gain design method to find observer gain such that this one has desired eigenvalues. All right, that's all we want. Okay, that's all I need you to know. So let me get you through that. Our goal is to find, the observer design goal is to find L such that eigenvalue of A minus LC equal to Eg desired. This is observer gain. Okay, I will tell you how to select these observer eigenvalues. Before we know, we want the closed loop eigenvalue to be some location, right? But observer eigenvalue typically need to be much more stable than the control eigenvalues. You want that to converge faster. Okay, that's our goal, and we don't know how to do it. What we know is we know how to design K such that A minus BK has desired eigenvalue. So let's do this. Let's define a new notation A tilde equal to A transpose, B tilde equal to C transpose. Can we do it? So we know how to find K tilde such that Eg A tilde minus B tilde K tilde equal to Eg desired. Can we do it? You can't, but you learned how to do it, right? You learned how to do it. Suppose you know it now. Is this the same? They're different for now, right? They're different things. B times the design variable K. Here is the design variable K times C. They're different. If C times L, L times C are completely different things, right? But we know how to do this. So we also know, you're supposed to know, by the way, eigenvalue of A tilde minus B tilde K tilde equal to eigenvalue of this A tilde B tilde K tilde transpose. Do you know this or not? A and A transpose, if the square matrix, right, has the same set of eigenvalues. Of course. Right? So you can just move it in, you get eigenvalues of A tilde transpose minus B tilde K tilde take transpose. You got K tilde transpose, B tilde transpose. Okay? Then this A tilde transpose is A, right? K tilde transpose times B tilde transpose is C. That's our definition. So we have this in the right place now. So we can choose L equal to K tilde transpose. So are you with me? This is our goal. We want to find this L. We don't know how to do it. Then we just use this A transpose, define it as A transpose, A tilde, B tilde. Eventually we find it out. Our design is of this form. We're done. Of course, you can use you can rederive everything again, but this tells you a shortcut to achieve our design goal. Any questions? All right, now we have the observer. Then we can, we have already learned how to do this. So the whole thing, procedure is the following. When you design your control, feedback control placement, K, and you design your L so that your observer also converges. So what eventually we have is the following. So you have your plant is your output. Here's your U, right? You need to determine this U. And the Y and this U somehow gets into this observer. Okay, this observer tells you what is your X hat. Is that your X? No, it's not your X, right? And this X hat to your state feedback gain times X. That gives you a control. Okay, that's your control design principle diagram. All right, you don't have access to state, you estimate it, and then you use that as if that's your, let me not use a expression, that's your control, state feedback control. Let's call it, let's just call that a function of u. It's function of the input, the u equal to, in this case, negative k times k hat, negative k times x hat. All right. So that's the whole design procedure. And one thing I want to mention, how much time I left? 4 minutes, right? Before quiz. You design your controller, place the closed loop gain. Place the closed loop eigenvalues, and then design your observer. And hopefully this guy will converge. But overall, you have a loop. Actually, these things are affecting each other. Okay? And a key feature of linear control is the so-called I don't know why it's slow, separation principle. Let me see whether it's so-called separation principle. Is that I can design my observer without thinking about my controller, okay? And I can design my controller without thinking about my observer, in the sense that I place my pose of closed loop control system. And I just think I have the full state, although I don't, right? You only have access to x hat, not sk, okay? But that you can think, you don't worry about controller, observer, you just have your full state. You design your k, the control part, you don't think about the observer, you think you have the true state, okay? That ability is actually called separation principle. And because you plug them in together, everything will work out. Okay, so that's the discussion of separation principle. I don't want to go through them very kind of seriously, but you can take a look. So eventually, if you, overall, okay, overall, this is your system. This is the plant. Let's say this is A sk plus B uk, and a yk, something like that. Sorry, this is xk plus 1 equal to this. All right, yk. So this is a dynamical system in Rn, right? N-dimensional dynamic system. But in the observer, you also have a dynamic system, right? This guy is xk hat is axk hat. Depending on what you choose as a state, that's the observer state. Okay, that's also a n-dimensional Rn dimension dynamic system. Okay, so overall you have R2n dimension dynamic system. Your state vector is actually xk and xk hat. All right, so the overall system, closed loop dynamics of joint state vector is actually xk and x hat of k. And this is the equivalent. You can use these two or xk versus x arrow, the difference between these two vectors, they are the same. Okay, they're all in R2n. So we can use this. You can derive the closed loop dynamics for this R2n whole overall dynamical system. And what you find out is that the closed loop dynamics of this form. I just want to mention one thing before we stop. The eigenvalue of this, the closed loop dynamics, is, this is, let's call it eigenvalues of this guy. Okay, I will just call this equals to the eigenvalue of block, let's call block 1, 2. Eigenvalues of block 1, union of eigenvalue of block 2. Okay, that's the, if it's not block, it's just number as everything works out. This block is also true. Okay, the eigenvalue is just the two block. If you have an upper triangular or lower triangular matrix, or block triangular matrix, the eigenvalue of the whole thing equal to the eigenvalue of blocks union together. And what it tells us that if the control is stable. The control gain is set stable. Observer is selected such that the observer is stable. Then the overall system automatically stable. In the sense that x will convert to 0, error will convert to 0. You see what I mean? All right, x convert to 0 and error will convert to 0. Actually, the x conversions actually depend on the error. There's a coupling term. The observer dynamics will affect the convergence of the closed loop, the control part. You see that? But eventually this part will die out. Only this eigenvalue matters. Okay. The reason, that's why also the observer gain should be much smaller or converts faster than the control gain. Because your control assume the action is right, the state is right. If the state is too far away from true state, then it's the inner loop has to converge faster than the outer loop. That's typical case. I wouldn't dive into that too much. The next lecture will purely on design examples. You will learn quite a bit on this part. I think I close this lecture. So we have a quiz, okay?